In this video, I'm going to be using R to construct some confidence intervals and look at hypothesis test results for some of our SLR parameters, and also just do a little bit more exploration as well. So I'm going to be using a data set called diabetes. It comes from a package called Fairway. So I'm going to load Fairway, and then I'm going to do a documentation search on diabetes. So whenever we're working with data and trying to draw inferences, we should first just know where the data comes from, who was in it, and what kinds of generalizations we really can make. So for example, this data, it has a lot of variables related to health, including cholesterol, HDL, let's see, age, gender, height, weight, a few other things, blood pressure. In the context, these are 403 African Americans were interviewed, and they were in Central Virginia, right? So if we're thinking about generalization, obviously we have to think about the particular sample that this comes from. Does this generalize to all races or ethnicities? Does it generalize to folks outside of Central Virginia, right? I don't know. So with that said, we should only kind of make these inferences with the understanding that it hopefully represents this particular community, but not necessarily everybody, say like in the United States. That would be kind of not necessarily the case. Okay. The other thing I'm going to do is I want to take a kind of have a glimpse of the data itself. So I could do that by typing in head diabetes, and I just kind of want to see the variables and what the data typically looks like. So instead of just kind of printing like 100 or more, I can just kind of print about 10 or so rows of data there. Now, typically at this point, if we were going to do a linear model, we should plot it first. However, I'm going to hold off on that because I think it's a little bit more interesting to look at the linear model results, talk about what we're seeing, and then kind of go back and think, what could this data look like? What do we expect that plot to look like given our linear model results? So, but typically if we were doing real analysis here, we would be plotting, I think we should plot everything before you ever run a model. So let's go ahead and create a model. So I'm going to do model, or I'll do mod to make it easier there. It's going to be a linear model, and I'm going to do cholesterol predicted from weight. That's something that I think would be interesting is, does weight serve as a linear predictor of cholesterol? And so it's coming from diabetes. So I've created that model. And now I can also run a summary of that model here as well. So summary of mod, and that's going to give me some helpful output. And so one thing that you'll see from summary, by the way, is results of the t-test for both intercept and slope. Now, even though we've talked about intercept, more often than not, we probably don't really care that much about the intercept t-test, about whether or not the intercept is significantly different from 0. The slope, though, is very consistently something that we care about making an inference for. Do we have evidence that the slope is non-zero? And so in this case, we get a slope estimate of 0.07363, meaning that for every 1 unit increase in weight, if this is measured in pounds, which I'm assuming it is, but maybe I'm wrong, maybe it's something different. Yeah, weight. So for every 1 unit increase in pound, we expect cholesterol level to go up on average by about 0.07363. So if you think about that contextually, that's not a very big difference. That doesn't seem to be much of a relationship. And sure enough, the t-test results are also very kind of non-excited, non-enthusiastic about this relationship either, meaning that this is kind of in that this could be explained by random chance. And it's a little bit on the low side, but still reasonably high. Like 18% of the time, we'll get this much correlation by random chance if there was no relationship. So really not much evidence there. So in case, just for a note about this t-test, so this t-value right here is found by taking your estimate, your coefficient, divided by the standard error. And that's the same case for this line as well. So if we divided 0.07 by 0.05, we would get 1.339. And if we do a t-test here, so I'm going to do pt of 1.339. My degrees of freedom here is 399 because there's about 401 rows, I suppose. Or I guess maybe there's 403 rows, but there's 2 that are missing values. and then we take off 2 more for degrees of freedom. So degrees of freedom is going to be 399. I don't want the lower tail here. I actually want the upper tail since I plugged in a positive value. So my one-sided p-value is going to be about 9%. And if I turn that into a two-sided p-value, it should be about 18%, which should match this value here. Okay, so let's talk about how do we extract values from this summary model, right? So if I want to do names of summary mod there, I'll get a list of all the different things that I could extract from the summary. The coefficients are probably going to be the most important. R squared is helpful. Maybe I might be interested in sigma. That would be the standard deviation for the residuals, or the F statistic, but coefficients is what I'm going to focus on here. So if I take summary of mod and then coefficients, I'm going to get a list of kind of this main part of the table. It's going to be my coefficients as well as the t-test results for those for significance from 0. So if I wanted to extract a particular coefficient here, I can do it one of 2 ways. Either I can treat this as a vector of 8 values. In other words, I can go anywhere from 1 to 8 and get one of these values. So it's going to start from here. This would be 1, 2, 3, 4, 5, 6, 7, 8. So if I wanted to go all the way to say like this t-value of 19.45, that would be the 5th entry if I'm going in order there. Something else that might be a little bit easier is I could do it also in terms of rows and columns. So if I want maybe the 2nd row, 4th column, that would be like this p-value for intercept. So 2nd row, 4th column, I could also enter it like this as well. So let me do that. And so I'm going to get this p-value of 18%. So either way, you can extract any of these values from kind of the main coefficient table there. You can also extract other values, but I won't do that here because these are not super important for this particular section of the content. Now, confidence intervals for parameters, that's certainly important. So if I wanted to calculate a confidence interval for beta naught or beta 1, there's a conf_int function that I can use where the first entry, I could just name the model that I've created. And then secondly, I can list the level of confidence that I want. So I could do 95%, I could do 90, I could do 99, I could do any, I could do whatever random value I want, I suppose. But I'll just go ahead and do 95. And this was going to produce to me a confidence interval for the parameters involved in this model, which is going to be the intercept and slope. And so you're going to notice that these 2 intervals are going to surround. They're going to be centered on my estimates 194 and 0.07. They should be equally distant in either direction from that. If I want to extract, again, a particular value from that, let's say that I want maybe just the first row, I could do that, I believe, by doing that. So if I just want the intercept intervals, I could do that, or the slope intervals. So you can kind of play around with these different brackets to, if you're curious in getting different specific extractions, you can just kind of play around with these options. Now, we could also do confidence intervals for a mean response given a particular x value. For that, though, we should use the predict functions. We've used predict before for our best estimate given a particular x value, right? So I could do weight equals 150. And if I don't have interval equals confidence here, right? So if I, oops, let me fix that there. So if I don't have this interval equals confidence, what it's going to do is just give me a best estimate. So I'm going to actually delete both of those. So I have my model name, I have my inputted x value, and I'm going to get a best estimate for y. But if I want to do a confidence interval, I'll do interval equals confidence. If I want to specify something besides 95%, I need to input it. I'll go ahead and do a 90% confidence interval for y, for the mean of y given x here. And so here I'm going to get, again, it's centered on 206. It's going to be 201 to 210 would be my 90% interval for the mean response of y. If I want to do a prediction interval, I would do the same thing here. Again, I would do weight equals some value that I'm interested in, and then I would just instead put prediction here and set my confidence level as I want. I'll do 90% for easy comparison, but this interval is going to be a lot wider because this is predicting where 90% of the possible y values should be contained in, as opposed to a 90% confidence interval for the mean response at that point. Okay, so at this point we are ready to go ahead and plot, at least for this video. Before I do that, I would really challenge you to kind of think, what do you think this plot looks like given the information that we've seen so far? If you want to pause, you can. Otherwise, I am going to plot here. And as we might expect, we have very weak linear relationship between weight and cholesterol. We have a lot of data, relatively. We have about 400 data points, meaning that if there really was a relationship, you would think we'd be able to see it by now. So the fact that there really isn't a clear relationship kind of matches why our p-value is not particularly low. If there is a relationship, it seems mild at best. And so I think we did a confidence interval for the slope earlier, right? Let me go back up here. So confidence interval for slope, we're going to notice that it probably overlaps 0 if I do a 95% interval. So again, just kind of suggesting if there is a relationship, it's probably pretty mild. Okay. So let's go ahead and also get in a line of best fit on here as well. But what I want to do is I want to do everything together here. So not only a line of best fit, but I'd also like to plot the confidence interval for the mean response of y, as well as prediction interval bands for y as well. So I'm going to do a couple things. First, I'm going to set a sequence of x values to work from. So I'm going to do basically the minimum weight value I have to the maximum weight value I have, and just create a sequence of every 1 unit. And I'm also going to save both my confidence interval and my prediction intervals under a name so that I can put them in my, my line functions coming up. So this part's just kind of set up for what I want to do here. Then I have my same plot followed by a line of best fit. So I'll go ahead and plot that. So here's my line of best fit. And then I have 4 line functions following. Each of them is starting with the input of grid. So grid is just my vector of x values progressively from the minimum to the maximum x value that I observed. Followed by the confidence interval lower value for each of these inputs. So basically, I'm taking confidence interval, but I'm plugging in this list of possible x values and outputting the lower bound of my confidence interval, and then doing the same thing for upper and doing the same thing for the prediction intervals as well. So then if I run these 4 lines as well on top, I'm going to have my mean response for y represented with this very narrow, hard to see bounds here. My prediction intervals are going to be these much wider lines out